So today we'll continue talking about hypothesis tests. We'll cover the last of the tests that you'll need in order to complete this week's homework assignment. And then time permitting, we've got the slides that you all submitted yesterday. So thanks everyone for getting those in on time. And we'll try to get through a review of all of those today. And if we don't get through all of them, we can carry those discussions over to Monday. So like I said, we're going to continue hypothesis testing. We'll talk specifically about the paired t-test today, which is appropriate when we have two samples that are not independent of one another in some respect. And then we'll come back to the term paper topic ideas that we started talking about on Monday. And then as a reminder, the first assignment is due midnight on Friday. I've left it relatively open. So I used to be a lot more prescriptive in terms of the format of the homework assignments. But I just want to make sure that everything is self-contained and I can easily follow your work and don't need to refer to the actual assignment document. So everything should be self-contained, your answers clearly labeled, and then your results described in terms of whether differences were statistically significant and then also what the test results mean in practical terms. So, and then secondly, the next deliverable will be for our term paper. And so we'll have an introduction section that will be due a week from Friday. And I'll post some additional details of that later today, along with a few quick example videos that'll demonstrate how to conduct these same tests that we've been doing over the past 3 weeks using Excel, okay? All right, so after today's lecture, you should be able to conduct a paired t-test, and in addition, you should be able to basically compare and contrast which of the different two sample tests of means is most appropriate based upon what we've talked about to date, and that would include determining whether or not we'd want to do an independent sample, which would be students or Welch's, or the dependent sample, which is the paired t-test, in consideration of whether the samples, again, are independent and whether the variances are equal or not, which would be the distinguishing factor between using students and Welch's. Okay. And so what we've got here are some sample data we'll use to work through a few of the examples today. And so basically, these are hypothetical crash data that have been developed, and we're assuming that signal timing adjustments have been implemented to try to improve progression through a traffic signal network. And prior to these improvements, there had been a significant number of rear-end collisions at these locations. And so what we see in the summary table here, we have data for 10 unique locations. In each of those cases, X sub 1 is the number of crashes that occurred during the year prior to those signal timing changes going into effect. And X2 for those same locations is the number of crashes that were experienced the year after those signal timings had gone into effect. And so just from looking at this, you'll notice that in general, we saw declines in crashes, but there is a fairly significant amount of variability from site to site here that we'll talk about in a few subsequent slides as well. Okay, so that's the setup essentially. Now, what we're going to do is basically we'll do a quick recap of the two sample tests we talked about previously using the same data set. And so if we assume those population variances are unknown, again, that would direct us to the t-test rather than the z-test. And secondly, if we assume the variances of the two populations are equal, we can then utilize students t. And as you should recall from last time, students t-test is just as indicated here, where the numerator, we're simply taking the difference in the sample mean. So based on the sample data from the preceding slide, this would be the mean number of crashes before and after the signal retimings. We're comparing those against some hypothesized difference of interest between those two populations from which the samples are drawn. In this case, we're just assessing whether or not there's any difference whatsoever. So just testing whether the difference based on our sample means is different from 0. And the standard error of that difference is as given in the denominator here. So we've got our pooled variance, which is basically just the weighted average of the sample variances for samples 1 and 2 respectively. and times 1 over the sum of their respective sample sizes. Okay, and so that test statistic will be distributed as T with degrees of freedom equal to N1 plus N2 minus 2, or N minus 1 for each of the individual samples respectively. Okay. And so, as I had indicated, we talked a little bit about this last time. So when we talk about degrees of freedom, that's basically telling us out of our entire sample, the number of values that are free to vary. So if we have to conduct intermediate calculations in order to calculate these test statistics, we need to subtract off a certain number of observations from that sample size, because some of those values are constrained. Because, for example, to calculate the variance, we would need to estimate the sample mean as an input to that. And so in the case of these t-tests, generally we'll lose 1 degree of freedom for each of those samples as the course of those intermediate calculations. And so in this specific application, as I had alluded to, our degrees of freedom, which you'll see denoted either as DF generally, or DOF, or as lowercase Greek letter nu, is going to be N1 plus N2 minus 2. And then we would go to our critical T table, and depending upon whether we were conducting a one-tailed or a two-tailed test, we would select the corresponding significance level from the top row here. And then as we read down the leftmost column, this is our degrees of freedom. And so we would just use this to identify the appropriate critical value that we would use for comparison purposes for students T. Okay. And as a reminder, the pooled variance that we had introduced previously is just going to be a weighted arithmetic average of the sample variances. And so basically we're weighting those by the respective sample sizes. The larger the sample, the more confident or reliable that respective estimate is. And so consequently, we'll give greater weight to the larger samples. And in the case where sample sizes are equal to one another, this is just a straight average of those respective sample sizes, as we see in this case. Okay. So again, pooled variance, just a ratio of the individual sample variances. And so if we work through with the sample data that we've seen previously, our mean for the first sample, so prior to the signal timing going into effect, those changes, we averaged 9.2 crashes per year, and the variance of those counts was equal to 7.73. And then likewise, the same calculations for the second sample. The sample mean for the second sample is 7.40, and the variance is 3.6. And so we can use that information in turn to calculate the pooled variance. And so both of our sample sizes in this case are equal to 10. And so we're just taking 10 minus 1 times the first sample variance plus 10 minus 1 times the second sample variance. And then we're dividing by N1 plus N2 minus 2. And that gives us a pooled variance of 5.67, okay? And so with that, we have all the information that is necessary to plug into our student t-test. And so plugging those numbers in directly, we'll find that our calculated value of T in this case is 1.69. And so in this specific case, we were basically assessing whether or not crashes went down, which is what we would anticipate would happen with these signal timing improvements. So there'd be fewer rear end crashes. And so as we think about the way this test is oriented, we would expect that this T statistic, if we reject the null, would tend to be very large in the positive direction. And so, you know, we're tending out towards this tail of the distribution, but we need to compare that to our critical value. Now, if this were a z-test, we would go down and compare to our critical value of 1.645. So we're pretty close there. But since we only have 10 observations in each of our respective samples, we're not going to be quite as confident. So we're going to need to increase the level and the magnitude of that critical value. And so the way we're going to do that, again, we're assuming N1 plus N2 minus 2, or 18 degrees of freedom. And so we read across to 0.05 for our significance level. We read down to degrees of freedom of 18, and that gives us a value of 1.734. And so we're not quite to that level. And so as a consequence, we cannot reject the null hypothesis in this case. And so that doesn't mean, again, that our signal timing changes haven't had an improvement or a positive impact on safety performance. It simply means that based upon the sample data that we're working with, we don't have sufficient evidence to claim that that result is statistically significant, okay? And so we can go through and conduct the same type of test using Welch's T. And as a reminder, the only primary difference here, we're again focusing on two samples that are independent, but in this case, we're assuming the variances are not equal to one another. And so Welch's T looks very similar to what we saw in the case of students' T. Again, the only primary difference here is that instead of a pooled variance, we have the individual variances in the numerator of the standard error term down here. And so calculation of this is going to be straightforward, and the only significant difference is that our degrees of freedom are not going to be quite as straightforward for us to determine in this case. And so working through with the same data we had just shown previously, we'd already calculated those respected sample means and variances. And so in this specific case, since our sample sizes are equal to one another, we're actually going to find that our calculated value for students in Welch's T are both equal to 1.69. And so the only substantive difference is in determining the appropriate critical values. And so in this, our degrees of freedom are calculated using this formula, which is, again, just the weighted average based on the sample sizes and the respective variances of those two samples. And in this case, we see we have reasonably large differences. So one sample variance is roughly twice as large as the other sample variance here. And so our degrees of freedom as a consequence are reduced from 18, which would be the highest possible value if those variances were exactly equal to one another, down to 15.89. Now, as you'll recall, we do want to be conservative. And so as a consequence, in determining whether we should use 15 or 16, we would round down to 15, which would basically require a larger critical value in order to reject the null. Okay, and so in determining that T statistic, this is slightly larger than the 1.734 value we saw for students' T. In this case, we need a value at least as large as 1.753. And since we saw on the preceding slide that our calculated T statistic is still 1.69, we're in the same circumstance as we were before. And that is that we cannot reject H naught. So we failed to reject the null, and we can't conclude that the signal timing changes have had a positive impact on crashes. Okay. All right. And so now we're in a bit of a situation because in both of these circumstances, there seem to be general trends that suggest that crashes had gone down consistently across many of those locations. Unfortunately, we weren't able to show that those were definitive based on, the underlying probability and statistics that we've been working with here. But there are a few important factors that we can think about here that may lead us to more robust analyses. And we could potentially reject that null hypothesis if we're better able to account for the variability that we're observing in those crash counts from location to location. Okay. So in this specific case, if we think about this hypothetically, in a number of settings in practice, we may observe observations between samples that are somehow correlated with one another. And that would typically arise in circumstances where we're observing the same individual or the same unit, or in this case, the same site over time. So for example, in this case, we've got 10 intersection locations. Some of those intersections tend to experience more crashes than others. Some of them tend to experience fewer crashes than others. And if we think about it in concept, it might be reasonable, even after these signal timing changes are implemented, that those higher crash locations would continue to be higher crash locations, while the lower crash locations would tend to remain and experience lower numbers of crashes, all other things being equal. And so that's essentially what we're going to assess here. And so under this scenario, we can think of those individual data elements between the two samples of being paired with one another or dependent on one another. And what that means, in essence, in this case, is that there are other factors that are unique to those sites that may cause crashes to go up or go down, but we're not explicitly accommodating those as a part of our analysis. And so what happens then essentially is that all just becomes noise or random error. And what we're often trying to do in statistics is to control for the amount of error that's present. And if we're able to attribute that error to different factors, we can help to minimize the amount of just purely random error or noise in our analysis. So when we think about the variability in our crash data in this case, some of that we can attribute to specific factors like the signal timing changes, for example, and then some of that is likely going to be due to factors that we don't have in our data set or we're not able to observe for whatever reason. And those could be site-specific factors, like here we might have different levels of traffic volume. We might have some geometric differences from site to site. There may be different land use characteristics. There are a whole bunch of things that could be different across those road segments. But if we're comparing the data before and after at an individual location, those differences are common. And so what we're doing in the paired t-test is we're, instead of just comparing the means and variances across the entire sample as though they're independent, we're looking at how much variability there is across the individual sites. Okay, so we're basically looking at average differences from site to site, which, as you'll see in the subsequent tests, is slightly different in context. We're addressing the same fundamental research question, but we're doing so under slightly different assumptions. Okay, and so in this case, we're just going to use what's referred to as a paired t-test. And the hypotheses that we're working with are generally going to be similar to one another. So we're going to just establish a mu sub d, which is going to, the d subscript is just going to refer to difference between those respective populations. And so our null in this case is that the mean difference is equal to 0, or that there's basically no effect of the signal retiming in this case. And then the alternative is either that they're not equal, or that difference is greater than 0, less than 0, depending upon whether we're looking at a one sample or a one tail or a two tail test. Okay. And so in order to calculate the paired t-test, first of all, we're going to simply take the differences between those respective samples. So as you look at the table on the right of the slide here, this difference d sub I is just simply x sub 1i minus x sub 2i for each of these intersections, which we've indexed from I equals 1 to 10. And so you'll see in all of these cases across all 10 locations, crashes had either remained stable or they had gone down. So we saw a difference, a reduction, when we take the before period count minus the after period count. And so since we essentially have taken those 20 observations and we've reduced them down to just 10 differences, the test we're going to apply here is basically completely analogous to just the one sample t-test that we had talked about previously. Okay, so instead of comparing the mean of a given sample to some population mean of interest, here we're just comparing the mean difference. So the mean of these 10 differences against a hypothesized difference of interest, which is just going to be 0 in this case. We're testing whether or not there's any difference whatsoever between those samples. And so that term basically drops out of the numerator. In the denominator, we just have an equation that's basically the standard error of the mean, except in this case, it's the standard error of those mean differences. And so we're just going to calculate the standard deviation of these 10 numbers, divide by the square root of the sample size. And then interpretation is going to be very similar to what we had done in the one sample t-test previously, okay? And so working through the calculations in this case, the average difference from the preceding table was just equal to 1.8. The standard deviation of those differences was equal to 1.55. And in this case, our denominator, that n is the number of pairs that we're working with. So to use this test, we're basically going to operate such that n1 is equal to n2 is equal to n. And so interestingly, our test statistic in this case is 3.67, which is significantly larger than what we had seen previously. And it may or may not be obvious why that's the case here, but this mean difference we see at the top, that 1.8 crashes per year, that's the exact same quantity we had seen previously in the numerator. And so the big difference here is that our variance, or our standard deviation, has been reduced significantly. And so the reason for that is that we had a lot of differences, as I had alluded to previously, from site to site. And so if we look back at that table, there were a number of sites that tended to experience, say, 10 to 12 crashes per year. And then there was another subset of sites that was more in the 4 to 7 range. And while crashes decrease consistently, they tend to remain in those same general ranges if we looked at those respective groups. And so consequently, what we tended to see in this case is that we would have significant variability across locations, but lesser variability within the individual locations here. And so as a consequence of that, since we've been able to explicitly control for those differences from site to site, because we've basically set this test up so that we're looking at differences internal to each of those sites. So we've kind of basically pulled out those differences across sites. And as a consequence of doing that, the variability in those differences is significantly smaller than the overall variability between the before and after period and across sites. And so we're controlling for the underlying variance in the data in a slightly different manner here. And the test statistic in this case is going to follow a t-distribution again, with n-1 degrees of freedom in this case. And so our critical t-value is just going to be n-1 or 10-1, so 9. And we would reject if this calculated value is greater than 1.833, which in this case it clearly is. And so as a consequence, we can reject our null. And in this case, we can claim that there is a significant difference between those samples. And as a consequence of that, it does appear that those signal timing changes had a positive impact from a safety perspective. Okay. Now, just to demonstrate a little bit further what some of the advantages or potential disadvantages of using the paired T are, we're going to revisit the exact same problem, but let's assume the data were collected by a researcher we had hired from the University of Michigan, for example. So they made some mistakes in transcribing the data, and so the numbers are the same here, the means are the same. But these data aren't actually paired, and we're instead treating them as if they are. And so you'll notice here, since those data have been transposed, we see a mix here. Crashes had actually went up at 3 of the sites, seemingly based on this data. It went down at 7 of the sites, but there's quite a bit more variability as we look at these differences within the sites here as well. So going through the same procedures, we would still see that same overall mean difference of 1.8, because keeping in mind that's just basically an average of the before crashes minus the average of the after crashes on an annual basis. But in this case, our standard deviation now is going to be significantly larger than it was previously. And so our calculated value, instead of being north of 3 in this case, is only equal to 1.62, which is in a very similar range to what we had seen previously when we calculated students and Welch's T. We've got the same critical value of 1.833. And so in this case, we're running the same test, but we've paired the data in a manner that doesn't really make sense because those pairs of observations aren't apparently correlated with one another. And so in this specific setting, we're back to where we were initially, and we don't have sufficient evidence to reject the null. Okay. And so this highlights an important point when we think about applying these respective paired t-tests. Okay, so the big picture takeaways here, it's appropriate to use the paired t-test in cases, as I had alluded to previously, where we're looking at the same individuals repeatedly over time. So we've got some type of what we refer to as a longitudinal study where we observe the same individuals at different time points. And so as a consequence of that, we also refer to this as a within subjects or repeated measures design. And that just means that we're basically comparing our dependent variable of interest here is being compared within the individual subjects rather than across subjects. And as the repeated measures name implies, we're just basically measuring the same dependent variable several times over some time period of interest, okay? And so when we think about this, the paired t-test is going to be more powerful, and you might want to think back a little bit when we talked about statistical power, but power is basically the probability that we would reject the null when the null is actually false, right? So we're rejecting correctly or when we should. And so we'd want to use the paired t when we've got strong positive correlation within those samples that are being compared, okay? So in this case, as I had alluded to previously, the high crash locations tended to experience more crashes both before and after those signal timing changes were implemented. And likewise, the lower crash locations tended to experience lower crashes during both of those respective periods. But we did see relatively consistent reductions within the sites between those periods. Okay. Another way to think about this is with respect to how large the variance of the differences is compared to the sample variances. And so we want to use the paired t when the variance of those differences is small. And in contrast, if the variance in the differences is large, as we saw in the application we just went through where those data were mixed up, in that case, it becomes less advantageous to us because what we're basically doing, as you had seen previously, the numerator is the same across each of those tests that we had applied. The only difference is in our ability to try to quantify what the standard error of that estimate is. And so basically, it's a function of how we're trying to handle that variance respectively, okay? And so with that being said, the one big trade-off we have here is with a paired t-test, we're basically having the available degrees of freedom. And so what are the practical implications of that? It basically means that we need to observe a larger difference or a larger test statistic in order to reject the null hypothesis. And so consequently, it's relatively straightforward and quick to just run the tests in both manners, so the paired and independent sample tests. In most situations, you'll find that the independent samples, so students or Welch's, will be more powerful tests, and then that the case where that isn't true is where we have some form of correlation. And I would say in most cases, it's straightforward to us when we're in the process of conducting that analysis that the data are formed or are paired in some form or fashion. So it would be, we won't necessarily, just because we have equal sample sizes, we won't immediately go and try to pair those data unless we thought there was something that was similar between those individual observations. Okay, and so we'll talk about that a little bit more moving forward, but that essentially gives you all the information you should need in order to complete the first homework assignment. And so at this point, it looks like we've saved a good amount of time. Hopefully we can get through all of the student project overviews, but I guess before we do that, do we have any questions from anyone in the audience?
Excuse me, Dr. Saulani, could you go back to slide 8?
Slide 8, sure, give me one sec. Apologies for all the animations we're having to go back through. Okay, slide 8.
So here's the student test, but the variance of the two samples are not equal to each other. So how we can use student tests in this case specifically?
Okay, so, and this follows up on a question that Jordan had asked last time. And so the selection of students versus Welch's T, again, is basically a function of how different those variances are from one another. And there are a few formal tests we can run to assess whether those variances are equal to one another. And we'll talk about those next week. But so, I mean, from just a fundamental perspective, I mean, you can obviously run students or Welch's in either case. The concern is whether or not you're selecting a test that's appropriate. So conceptually, as we saw here, the results of the test, whether we use students or Welch's, we get the exact same answer for the test statistic, right? And so the only difference here is determining the critical value. And so basically our risk here, if we use students, we're assuming that we have 18 degrees of freedom to work with, where since these variances are rather different from one another, it appears that we should be more conservative and set a higher value. And so we should assume 15 rather than 18 degrees of freedom. And so what that basically means from a practical perspective is we could potentially use students' tasks and then we could reject the null when we shouldn't, because those variances are different from one another. And that, again, is just relating back to the fact that, and what we'll tend to find, we talked a little bit about this on Monday, as your samples get significantly larger, these differences go away rather drastically, and unless you see some very large differences with respect to your sample variances. But like I said, in a lot of the common statistical analysis software packages, it will run both students and Welch's, and in parallel with that, it'll run a test to compare the variances and tell you which of those is more appropriate. And so hopefully that has answered your question there. I guess the short of it is that we can formally compare the variances, but I haven't taught you how to do that yet, in essence. Okay.
So in case of student test, are the variances required to be identical, or even when they are close enough to each other, we can use student test confidently?
So, I mean, it's tough for me to give a universal answer that would apply across all scenarios here. In most cases where you have reasonably large samples, you're not going to see a very meaningful difference between these. It's in specific cases, like the example we see right here, where we have only 10 observations per sample, that those results will tend to diverge significantly from one another. And so particularly if you have lower samples, and if I want to throw out a ballpark number, I would say less than 25 or 30 in each of those individual groups, and you'd want to be more cognizant of differences here. As we start getting the cases where we have hundreds or thousands of observations, it's really not going to make a big difference. Now, if we wanted to be conservative, strictly speaking, the most conservative way to evaluate this is just to always use Welch's test, because Welch's test is always going to give us a more conservative answer than students' test is, with the one exception: if the variances are exactly equal to one another, we'll end up with the exact same test result.
Yeah.
So I guess my general suggestion would be to use Welch's. But again, it depends on the context. Generally speaking, you're not going to see the large differences between those results. Does that make sense?
Yeah, great. Thank you.
Okay. Yep. Any other questions from the audience?
Yes, I have a question about the two-tailed and one-tailed test. So most of the tests that we did recently are the one-tailed test. We are trying to see if the mean is greater or less. So is there any practical example, like traffic engineering example, where we are going to use a two-tailed test?
So in short, I had one small issue I wanted to correct here. And so, like in this case, the alternative hypothesis we actually used in this case was that mean difference was greater than 0. So we conducted a one-tailed in this test. So I'm just going to make a note to myself to come back, and I'll illustrate that any of those 3 hypotheses would be appropriate here. Now, to your broader question, Falarin, determining whether to use a one-sided or a two-sided test is largely going to be a function of whatever prior knowledge we have or prior expectations we would have in terms of the direction of that relationship. And so, for example, the cases we've talked about up to this point, so where we had the helmet law change or where we had the signal timing changes that were meant to improve safety, we had a fairly good idea of what direction that effect would fall. In the event we did reject the null, or we found that there was an effect of those respective changes. Oftentimes in research, we may conduct evaluations where we have some uncertainty as to what the direction of an effect would be, or what changes would be observed if something has an effect. And let's try to think of an example there. Let's say hypothetically we were looking at so speed feedback signs are an example. So we've done some evaluative work that looks at driver response to speed feedback signs. And in general, it's hypothesized that those would tend to reduce travel speed. So drivers basically see their speed. They may get paranoid that they could be monitored by law enforcement, and so they drop their speeds as a consequence. But there's also the scenario, some people will just try to see how fast they can go as a consequence when they're driving by those respective signs. And so I don't know if that's the clearest example, but that's a case where we might not necessarily see the effect that we had expected. Likewise, if we are, well, here's a good practical example. The introduction of self-driving vehicles. So at low penetration rates, I think there's still a good bit of uncertainty in terms of whether or not crashes will go up, down, or stay relatively stable as these are introduced at relatively low penetration rates. And the reason for that is that these vehicles tend to drive differently than other types of vehicles. And so if we think about things like the speeds that they select, so you might program a self-driving vehicle so that it's going at the speed limit, which would make the drivers behind it probably a little bit more aggressive as a consequence. And so if you look at crash data from self-driving vehicles, the number of crashes in which that vehicle is basically at fault in crashes is very, very low. But you see a fair number of crashes that are due to problems from other drivers or mistakes by other drivers based on their interaction with those self-driving vehicles. And so from a practical perspective, when we look at a one-sided versus a two-sided test, the one big difference is that we don't need to observe as large of a test statistic in order to reject a one-sided test, right? And so in the case of a two-sided test, our critical values would be, if alpha is 0.05, they'd be plus or minus 1.96. Whereas if we knew in advance that there was only one direction of interest, or we knew what the direction of that relationship would be, then our critical value to reject would only be 1.645. And so ideally, we like to design our experiments so that they're as efficient as possible. So we conduct them at lowest cost. We collect just as much data as we need, for example. And so as we set about planning experiments, if there is something that we don't have a good idea of what the impacts would be, or we have considerable uncertainty, I would suggest planning to conduct a two-sided test. But if we have significant confidence in terms of what the direction of that relationship would be, then I would suggest a one-sided test. Okay, but there's basically, there's a drawback, we're making a compromise from a practical perspective in terms of how we would conduct those tests. Does that make sense?
Yeah, very well. Yeah, I understand.
Okay. Other questions from anybody? Okay, if not, I'm going to pull the slides back up, and we're basically, these are all going to show up in alphabetical order, and we're just going to basically have everyone briefly talk through what they're planning to do as a part of their study, and then we can provide a little bit of commentary and feedback to assist in thinking about how we could conduct these studies over the course of the semester. So with that, Falarin, I guess you still have the floor.
Okay, so for my term paper, I'm looking at how the effectiveness of forward collision warning and autonomous emergency braking system vary by vehicle make and model. So for that, I'll be using the IHS crash testing data for the AEB, which is the autonomous emergency braking and forward collision warning tests. So they have data for about 325 vehicles, and for 2013 to 2021 model year from 2 different tests. So the key metrics I'm considering to evaluate was when the forward collision warning was engaged during the test. That's how early you get the warning. And then also for each vehicle, whether the AEB was activated, and if it wasn't activated, was there an impact? And then, and also the impact speed for the vehicle. So, I believe that the how efficient the AEB is will be related to the impact speed. And then I just pretty much developed like a kind of like regression equation, because they have different test speeds. So most likely the higher test speeds will also have an higher impact speed, to develop an regression equation to use impact speed to determine the effectiveness of the AEB system.
Okay, so thanks, Falarin. I don't know if anybody has questions or comments, and so just to kind of restate here. So these are basically 2 types of advanced driver assistance systems that have been installed in increasing numbers of the vehicle fleet. And so some of you may have these installed in your own vehicles, but basically forward collision warning is just a case where you have sensors, which could include LiDAR, radar, video, any combination of those, that are monitoring the driving environment in front of you. And if they detect an object that you're approaching at a great rate of speed, it can basically trigger a warning, and that warning could be audible, or it could simply, in my case of one of my vehicles, a light shows up when that's about to activate. And then after the forward collision warning activates, if that rate of speed continues and you're still approaching that object at high speed, automatic emergency braking can go into effect where the vehicle will basically start braking. And so Folarin has access to test data under several different scenarios, which would include a case where a vehicle is approaching another vehicle and there's a risk of rear end collision. And there are also some scenarios where basically there's a pedestrian, in this case it's a mock, it's not a real pedestrian, is either walking along the roadway or crossing the roadway. And so the vehicle will also engage these features in response to those. And so as we think about the other information Folarin has, he had indicated there's different test speeds that are utilized here, different lighting conditions, different makes and models of vehicles. Each of those makes and models would have different types of sensors, different sensor locations. And so what he's aiming to do here is to try to determine, what circumstances lead to better or poorer performance of those systems, basically, right, Folarin?
Yeah, generally that's the idea I have.
Okay. And so I think that should be a really interesting project. And I guess I'd have a better sense once we start getting a little bit further into it. But I think one thing that would be interesting to compare with respect to the makes and models. So if we think about it, even with the paired t-test example here, we'd have some variability from test to test in terms of the performance here. And then we'd also be concerned in comparisons across those different vehicle types as well. And I'd be particularly interested to see if certain types of sensor configurations show better performance than others. Because I know in some cases, the sensors are installed at different locations in the vehicle. And in some cases, it's using radar and video or just video or whatever the case may be. So I think there's some really interesting stuff we can look at there. Any other thoughts from the audience on this one? Okay. Thank you, Folarin. Nishal, want to give us the quick overview of your study?
So the research question that I'm trying to address is basically how the traffic speeds are affected by changes in, traffic safety is affected by changes in traffic speeds following the speed limit increase. So a little background. So in 2017, the state of Michigan increased the posted speed limits from 70 to 75 miles per hour on about 615 miles of freeways and from 55 to 65 miles per hour on about 943 miles of two-lane highways. So these increases have generally affected both traffic safety and operations. So I'll be basically trying to relate the crash trends with the speed limit increases as well as changes in speed profiles on these highways. So in terms of data requirements, the crash data will be obtained from the Michigan State Police for the sites where the speed limits have increased, as well as for a group of similar sites where there is no increase in the speed limits. So these will be our control sites. The speed data for the before and after period will also be needed, and the MSU team is collecting that data on an yearly basis. The crash and speed data will be integrated with the roadway data, which is available through MDOT, which includes roadway geometry and traffic data such as traffic volume. Yep, thank you.
All right, thanks, Nishal. And so one of the challenges with Nishal's study is we have a very robust roadway inventory database and traffic volume database, and we can overlay crashes onto that. And so we have good information we can relate to try to evaluate safety performance, irrespective of speeds. Now, the speed data and trying to integrate that is a bit more challenging because most of the speed data we're observing at a given point. So we don't have, generally speaking, full coverage of speed data across that entire road network. And so one of the challenges here is how we try to take speeds that are measured at individual points and extrapolate that broadly across the network. And so that's going to be one of the challenges we try to work with here. And then Nishal had also indicated that we have control sites that we'll be monitoring here as well. And one of the concerns that comes with speed limit increases, it's been hypothesized that there could be spillover effects, is how they're often referred to, where speeds can increase even on the sites where the limits hadn't been increased, just because people are driving faster at other locations. And so just generally speaking, people may drive faster as a consequence. And so that's one of the potential confounding factors we're trying to control for here as well. And then one of the other big challenges, or I guess two big challenges that I don't have a good sense of how we deal with at this point, is that marijuana was legalized, roughly a year ago now. And that may have some influence here. And then secondly, we had a pandemic occur in the midst of this analysis period. And so it'll be interesting to see how we can potentially navigate around some of those. So those would be cases where we'd see significant variability in, crash measures, probably in speed measures as well during our analysis period there. And so unfortunately, that gets back to the fact we can't really do controlled experiments. So we're largely doing observational studies, and these were some unforeseen changes that will probably make this and several of the any other study that's using 2020 data specifically a bit of a challenge. But anyway, thanks for that, Nishal. Any other questions, comments for Nishal? Okay, thank you very much. Emma.
Hi. So my question of interest, just how does the safety of roundabouts compare to traditional intersection configurations in the state of Michigan? I already have most of this data, but the roundabout location list also has like information of like the year installed, etc. It's from roundabout documents from MDOT, and then crash data for each intersection is from Michigan Traffic Crash Facts. And then the additional data needed would just be the AADT data of intersections of the roundabouts and like comparable traditional intersections.
Okay, great. And so the setup for Emma's is similar in some respects to what we just heard about for the case of Nishal. And so in a lot of these cases, some of these roundabouts have been converted from, say, traffic signals to roundabouts. And so in those cases, we can do a before-after type evaluation, like we did with the paired t-test, for example, today, although with a bit more complexity in terms of the methods that we would apply. Some of the challenges that are going to arise here is trying to identify good comparison locations. So in an ideal world, we'd like to know if your traffic volumes and everything else is the same, this is how crashes would vary for roundabouts versus a signalized intersection. And so trying to match locations based upon common characteristics is going to be an important concern here. And then there are also some factors like novelty effects. And so I don't know how much this is borne out by empirical data, but hypothetically, people have speculated that roundabout performance is poorer initially as drivers familiarize themselves with roundabouts. And many of you have driven through roundabouts where people yield when they shouldn't or don't yield when they should. And so we'll also be collecting some operational data as a part of this study. But Emma's work will focus specifically on what the safety impacts are. And another area to investigate is performance across different types of roundabouts. So if we look at single lane versus double lane versus 3 circulating lanes, we'll see significant differences in safety performance across those different scenarios. And so those are some of the questions that Emma will be able to hopefully address as a part of this study. So thank you, Emma. Jordan.
Okay, so I'm going to be looking at how the effectiveness of driveway assistance devices varies by location and then configuration, signage, like the auxiliary signs. My data is going to be coming from a field study that was conducted last summer, and we have like 2,200 observations at 10 different locations using 6 different sign combinations and a lot of data, but the main points are going to be like the direction, the legality, and the safety of the movement observed. And some additional data that could be useful for evaluating the hypothesis would be vehicle type data, whether the vehicle stopped, some characteristics of the site, gap, dwell, and queuing times, and then whether a vehicle proceeded or joined a platoon. And then also, I didn't list it here, but like length of queue could be interesting, and like signal head size was also varied on the DAD, so that could be part of the configuration.
All right, thanks, Jordan. Yeah, there's a lot of interesting stuff you should be able to look at here. I think one of my concerns here would just be, I think the setups are generally such that we can identify virtually any of the important variables we would need from the video. I guess the concern would be if there are things that are happening that would be affecting driver behavior that we can't see based on our camera setup. But I think by and large, this is set up fairly nicely. It's a quasi-experimental design, even I would say. A few of these variables, like the full stop condition, like that's tricky because oftentimes people don't come to a full stop. So what do you do in the case where it's not quite a full stop? So there'll be a bit of any of these cases where we're trying to classify driver behavior into discrete groups or categories. It gets a little bit challenging potentially, but anyway, it looks like we've got a fairly good sample size here, and we should be able to get some really useful insights here that will hopefully help to guide subsequent implementation decisions nationally. And so hopefully everyone was able to attend Jordan's presentation last week, and I'll be posting details of that to the D2L site as well. So everyone's got additional insights as to what we will potentially be looking at there. So thank you, Jordan. All right, Travis.
Okay, so the question that I'm looking at is, how does the impact of driver speed feedback signs at ramp curves vary based on the font size? So we collected data with both signs of 15-inch font size and 18-inch font size. We'll be able to compare those two. The sign position, there's a sign position just typically off the right side of the ramp on the shoulder there, and then alternatively one posted like near the first chevron over to the left side of the ramp. And the presence of an MDOT speed trailer, which there were some days of collection where it was present but not turned on, not activated. We just wanted to take a look and see if that had any real impact on driver speeds. We collected speed and braking data under all of these conditions this past summer and fall. And the additional data we used, we collected the vehicle type and then tracked vehicles as they traveled through the ramp. We collected the vehicle speed, I think like 850 feet upstream of the sign, and then one at the point of curvature.
Okay, very good. So yeah, with this type of evaluation, this is reasonably straightforward. I think the two areas I would be concerned with, and it sounds like we've got some plans for investigating these. First of all, would be a potential novelty effect. So when these signs are first installed, drivers may initially react more than they would over time. So maybe their behavior reverts back. And if the sign's been there for a few weeks or a few months, speeds might start creeping up a little bit. I know we've got longitudinal data over time at these sites. So that's something we can directly try to assess and control for. And then the second point was just the fact that we have these large data collection trailers that are being used to collect this information. And so not knowing whether the data collection devices themselves may have an influence. And that's something that, can potentially be a concern with some of the field studies that we conduct there. So, but by and large, I think we're in pretty good shape for this one. So thank you very much, Travis, for that overview. All right, Farish.
Hello. Right. So my question is how economic performances affects various operational and service measures of ferry systems. So by economic performances, we mainly mean fundings. So fundings can come in the form of fare box. For any given fiscal year, it can come from the previous year fare box revenue, local funding, state funding, and federal funding. So we're trying to see how these level of fundings affects the ferry operators' operational service measures. It can be the frequency, the total fare box revenue generated as a consequence, or the total volume of ridership it yields. So one can argue it can go either way. the services would affect the funding generated, or the funding would affect the service being provided. So we're open to both ends at this point, but so far we're going upstream. So the data sources would be mainly from NCFO, Census for Ferry Operators. On the first column on the left, it's the data type, the operator, segments, terminal, and vessel. So what these data types are contained, mostly about their operations, specific operations of the trips, segment length, average trip, total passenger volume, seasonalities. We also have details about the terminals, and we also have details about the vessels, what type of vessel, what type of fuel, the average speed, the capacity. So that's pretty useful. I think that's all we need for this analysis. But additional data would include previously conducted studies by AMDOT, which is quite outdated, I would say, but nevertheless worth looking for. We can also take a look at labor employment statistics if there's any supplementary data or analysis that we can do. And also we can use BEA, Bureau of Economic Analysis, for GDP consumer spendings, and to see if there's any anomalies or any other externalities that we might want to consider. That's all. Thanks.
All right, thanks, Barish. And so I've thought a little bit more about your specific topic area here, and I think one thing you want to look at in the near term is how much variability we see in these different measures within the same ferry operations over time, because there are at least two different ways we can try to approach this just from a methodological standpoint. One would be to try to assess what the differences or the impacts of changes at individual ferry operations would be over time. Now, in order to investigate that, we need to make sure that there are enough changes across these different sites that we could find, meaningful, I'd hesitate to say they're causal relationships necessarily, but, variable X changes and Y changes as a consequence of that. So that's what we're aiming for. If we find that a lot of these parameters tend to be very stable over time, then instead we might want to contrast performances across different types or different individual ferry operations. And what we may ultimately doing is a combination of the two, but there are slightly different assumptions that are introduced and slightly different methods that we'll talk about as we get further into the course. But it sounds like there should be some fairly good data available here. So looking forward to learning more about this. Thanks, Barish.
That's brilliant. Thanks, appreciate it.
Yep. All right, Isan.
Hi everyone, my question is, how is driver behavior impacted by collision avoidance and mitigation system on snowplows? The data source that I'm going to use is the data gathered by MDOT's collision avoidance and mitigation system, which is implemented on MDOT's snowplows. It consists of radar and also a warning system. So I think, and we have two data sets. In one of them, the alarm system is activated, and in another one it is not. So we can compare these two data sets with each other to evaluate the impact of this system on driver behavior. And also the additional data that I'm going to use is ADL data to capture the trajectories of the snowplows and vehicles and the other vehicles. And also, I think that's enough. But if we have weather conditions during the data collection period, because data collection period is, I think, around 2 weeks or 3 weeks. So if we have weather conditions during that time, we can also cluster the trajectories based on the weather condition, and also get the impact of weather condition on the driver behavior too.
Okay, thanks, Asan. And so just to clarify for everybody, so we had a study that was completed a few years ago where There were basically warning devices installed on snowplows where lights would be activated to alert drivers that they were approaching the plow at a relatively high rate of speed. And so there are thresholds based upon distance and speed acceleration profiles when that system was activated. And so as Asan had alluded to, we also have control data for a plow where that system wasn't equipped. And so we should hopefully be able to get some interesting insights here. One of the concerns, I guess, that you'll deal with, Asan, is just that data tends to be a little bit noisy. And so just there'll be a bit of quality assurance, quality control review. I think a lot of that's probably already been done, fortunately. But if we can get the data cleaned up, I think there's some promising directions we can go with this. So it sounds like a good study. Thank you. All right, Emily.
All right. So my question is, how have travel levels changed as a result of the COVID-19 pandemic? And so my motivation with this question kind of stems from my area and looking at how the impacts would be on the electric grid interactions, but I also thought this would be important for transportation because from what I've been hearing, people are moving from places like New York and San Francisco to places like Atlanta, Arizona, Texas, and they're still looking into big cities, but it seems that they're places of more space. And so what I was looking to do was look at the device totals per county between pre-COVID and post-COVID times, and then comparing that to the fluctuation during pre-pandemic time periods. And this would be provided by Cubic. And if it's not available there, I was thinking it'd be in Streetlight Data or SafeGraph, or I'm sure there's many other sites that are similar. And some additional data I was thinking of looking at was the population data, how sprawled out the cities or the areas are, and access to public transportation. So that was my understanding of this.
Okay, that sounds good. I'll probably have you follow up with one of my students, Anshu Bomni, who has led some of the data collection. He's actually sitting in here and auditing right now, but we've collected a lot of data, and I know there are data elements we haven't looked at in great detail now. So I think it would make sense to put you two in touch with one another. And it sounds like you are aware of some additional data sources that we've not utilized up to this point. And so there's a wealth of interesting questions we could identify related just to changes in behavior as a function of the pandemic. And so I think this sounds really interesting, and I guess we should be in pretty good shape moving forward. And like I said, happy to assist with coordinating data integration with Streetlight and some of these other data vendors as well. So thanks, Emily. All right, Jonathan K.
Going. So my paper is going to be looking at the safety performance of unsignalized median U-turn intersections. We've also got some data on signalized, but just for this class, I'm going to focus on the unsignalized side. And you can see, if you look at the figures at the bottom there, a typical scenario where you've got a conventional divided situation on the left where you've got that median opening that allows direct left turn movements from all four approaches, and then that gets converted to the situation on the right where the median opening at the intersection gets closed, and then you need to make an indirect movement for all the left turns as well as the through movement from the Minor Street approach. Data is going, it has been collected, and I'm still collecting some stuff in it from a whole bunch of resources, including crash data from the Michigan State Police. Traffic volume data comes from both state and local resources, basically wherever I can find it, particularly for the Minor Street approaches that can be somewhat challenging. And then also a whole bunch of stuff from satellite and street view imagery. The analysis ultimately is going to try to develop some safety performance functions and crash modification factors that are specific to MUTs. And then also going to compare both the before and after approach and cross-sectional methods. So one of the nice things about the unsignalized side is we actually have enough data to do a before and after evaluation, whereas on the signalized side of things, we don't necessarily have, a lot of the conversions have been in place for a really long time, so we don't have the before period data. So on the unsignalized side, you can kind of compare and contrast how before and after compares to the cross-sectional analysis.
All right, thanks, John. And so I guess just for everyone's context, one of the big challenges here, so trying to evaluate the safety performance between this type of setup where we allow vehicles to turn left across the median here versus this instance where we prohibit left turns and require U-turns. And so it just becomes a bit of a challenge trying to integrate the crash data and figure out how to make this an apples to apples comparison, because instead of crashes occurring in this area, they're now occurring in these two areas. And so there's quite a bit of effort required in trying to tease out, potential causative relationships on that basis, or shifts in the number and location of crashes. But this is certainly an area that's of great interest, and so hopefully we see some good results here. Thanks, John.
Mm-hmm.
All right, Jesse Liu.
Okay. Hi. So due to data availability issues, Dr. Sabelani suggests that I focus my question of interest on looking at the relationship between crash rates and roadway locations in Michigan. I only did a quick search, and it seems like I can find most of the data on Michigan Traffic Crash Fact database. And some additional factors I might investigate will include crash type and highway class, and also crash severity.
Okay, thanks, Jesse. Yeah, so in your case, all the crash data should be fairly easy to get from the MTCF website. The one thing we'll want to collect in addition would be traffic volume information, and so we can help work with you to figure out what would be the easiest way to easily integrate the crash and volume information for different types of facilities. And so it probably makes sense to focus primarily on the Michigan DOT network, just because it'll be easier for us to get traffic volume there. But we can talk through, how large of a scope we want here in terms of different types of locations. But I think this will definitely be an interesting topic to look at. So thank you, Jesse. All right, Hamid Mosafari.
Hi, everyone. The question that I'm going to work on is, how does the severity of crashes vary across a vehicle type? For everything? The data that can be used for the evaluation for answering this question is the number of crashes that happen in a state or across whole of the country, the severity of the crashes, also the number of each vehicle type which is involved in each of that crashes. The data sources that I found were these two ones. One of them was HCS, which is Highway Safety Information System, that consists of some data from some states of the US, and the other is FHWA, which is Federal Highway Administration. And the additional data that could be useful and have some effects on the evaluation is the age and gender of the drivers. Also, the weather condition at the time of crash could have some effect on the results. Just this.
All right, thanks, Hamid. Yeah, this is a good topic. You might also want to look at Michigan Traffic Crash Facts, would have most of this information specific to Michigan roadways, and there are a few federal databases maintained by the National Highway Traffic Safety Administration that could also be used for this form of analysis. So I'm happy to share further details of those specific data sources, but I think this should be something that'll be interesting to investigate. Thank you. All right, Babak.
Hi everyone, my research question for my project is about how road users feel about sharing road with autonomous vehicles. There have already been some previous studies in this area, and I'm willing to advance those studies. And the data that I'm willing to use is using like online survey data sets from United States or Europe. I have found some data sets already, and I'm willing to look more to find some more efficient and extensive data sets. And the kind of data that I need is like the general sense of safety among travelers while sharing road with AVs, and additional data are about how these users are familiar with technology. Either they are in favor of AVs, they know their benefits or risks or failures, such as the crashes that have occurred across the United States, the privacy or policy issues in this world of AVs, and also some additional information about the user type, their information, age, gender, income level. I believe this information will also be useful for this study or the view of users on the specific limitation for AVs, and either they have had a previous experience of sharing road with AVs or using an AV. Well, currently throughout testing AVs in different environments across the United States, some people have had experience of sharing road with these vehicles, and previous studies have shown that also this experience is also improving the acceptability of AVs. And I'm willing to look more into that throughout this study.
Okay, and so this is an interesting study, Babak. One other area you might want to look into, so Michigan State had actually conducted some survey work, I think it was back in maybe 2016, 2017 at this point. And so we have results from a state of the state survey of roughly 1,000 Michigan residents that gives their opinions on concerns and benefits they would see from self-driving vehicles. So I can share that data set with you as well, because that would give you a little bit of a local flavor, and there's quite a bit of additional information that would be of use there. And there'd still be an opportunity, I think, to publish there as well. So I will forward that information on, but this will continue to be an important issue. So getting feedback from road users about their views on interacting with autonomous vehicles. So thank you very much. Okay, Amirali.
Hi. So the question of interest is what subsets of drivers are most prone to involvement in different types of crashes. Speaking of different types of crashes, it could be categorized based on the severity or the number of cars involved in the crash, like one vehicle versus multiple vehicle crash. On the driver's side, the different characteristics that could be considered is like their age, gender, seatbelt use, whether they're driving alone or with passengers, whether they're driving under the influence or not, and if available, their source of distractions or their occupations. And the other additional data that could be considered is the vehicle type, spatiotemporal distribution of crashes, roadway types and condition, and weather and light conditions of the time of crash. The data sources I think about to utilize is the Michigan Traffic Crash Facts and also the FARS by NHTSA, if I pronounce it correct. But also I appreciate if anyone have any feedback on the definition of the question of interest or utilization of any available data source that could be helpful. Thank you.
Okay, thanks, Amirali. Yeah, Crash Facts would probably be a good place to start here, and then some of those same federal data sources I had referred to previously would also be of interest here. FARS is somewhat challenging because that's not a random sample of crashes. Those are all fatals. And so we'd need to think a little bit about the types of questions we would investigate there would be somewhat different than a database that would include all types of crashes. But in any case, this is an interesting topic and look forward to hearing more about it. So, okay, so we managed to finish right on time. It's 9:50, so I will get these slides posted, and then as indicated earlier, I'll have a few quick videos just demonstrating how to conduct the various types of tests we've talked about to this point in Microsoft Excel. The first assignment is due midnight Friday, and you'll also be getting details about the term paper introduction, which will be due next week. Okay, so thanks everybody. Have a great week. And if you have any questions on the homework, just feel free to get in touch with me. Okay, thanks.